Welcome to the lecture on trigonometric integrals. At the moment, our inventory of integrals involving trigonometric functions is rather limited. For example, we can integrate something as the integral of cosine of 3x dx very easily. We just notice that this is a u substitution problem, where u equals 3x. du is simply going to be 3 dx, or just a third du equals dx. We can rewrite this to be a third the integral of cosine of u du. This will be equal to, the antiderivative of cosine is sine, so this becomes 1/3 the sine of u plus an arbitrary constant of c, and this simply becomes 1/3 sine of 3x plus the arbitrary constant of c. As it turns out, integrals of powers of trigonometric functions are also important. And the goal of this section is to develop techniques for integrating integrals involving trigonometric functions. These techniques are indispensable when we use trigonometric substitutions in the next section. Let's take a look at this example. Let's say we want to find the integral of cosine cubed of x dx. We can split up the cosine cubed of x to be equal to the integral of cosine squared of x times the cosine of x dx. And now, if we recall a property from pre-calculus, which says if we have sine squared of x plus cosine squared of x equals 1, then of course this is the exact same thing as saying cosine squared of x equals 1 minus sine squared of x, just by subtracting sine of x squared from both sides. So what we can do is we can say this is the integral of 1 minus sine squared of x times cosine of x dx. Now what we can do is we can use a little bit of u substitution. So if I say u is equal to the sine of x, well then du is simply going to be equal to the cosine of x dx. So now this is going to be equal to the integral of 1 minus u squared du, because the du part takes care of the cosine of x dx, and then my u is simply going to be sine of x. Now, of course, this is very easy to integrate. This just becomes u minus a third u cubed plus an arbitrary constant of c. If I substitute my u back in, I'm going to get sine of x minus a third sine cubed of x plus my arbitrary constant of c. In general, we try to write an integrand involving powers of sine and cosine in a form where we have only one sine factor and the remainder of the expression in terms of cosine, or only one cosine factor and the remainder of the expression in terms of sine. Let's take a look at this example. Let's say we want to find the integral of cosine to the 5th of x dx. Well, let's rewrite this to be the integral of cosine to the fourth of x times the cosine of x dx. We can also rewrite this to be the integral of cosine squared of x squared, quantity squared, times the cosine of x dx. Now, if we use the substitution that we had before, we can say that the cosine squared of x is equal to 1 minus sine squared of x. I'm going to replace that here. So I'm going to get, this is going to be the integral of 1 minus sine squared of x squared times my cosine of x dx. So now again, if I use a little bit of u substitution, if I say u is equal to sine of x, then du will simply be equal to the cosine of x dx, and I can say this is going to be equal to the integral of 1 minus u squared squared dx. Now, working out the algebra here, this becomes the integral of 1 minus u squared times 1 minus u squared du. Oh, and this should be a du. Sorry about that. This, of course, becomes the integral of 1 minus 2u squared plus u to the fourth. The antiderivative will simply be u minus 2/3 u cubed plus 1/5 u to the fifth plus arbitrary constant of c. U was my sine of x, so this will now simply be the sine of x minus 2/3 sine cubed of x plus 1/5 sine to the fifth of x plus my arbitrary constant of c. Okay, let's see the integral of sine to the fifth of x cosine squared of x dx. Let's rewrite this to be the integral of sine to the fourth of x cosine squared of x times sine of x dx. We can, of course, say that this is equal to the integral of sine squared of x squared times the cosine squared of x times sine of x dx. Now, of course, this can be replaced by saying we have the integral of 1 minus cosine squared of x squared times the cosine squared of x times sine of x dx. Okay? So now let's use some u substitution on this. Let's say u is going to be equal to the cosine of x. Then du will simply be equal to negative sine of x dx, which is the same as saying negative du equals sine of x dx. So we can rewrite the integral to be negative the integral of 1 minus u squared squared times u squared du. Now working out the algebra, this is going to be negative the integral of 1 minus u squared times 1 minus u squared times u squared du, which will be equal to negative the integral of 1 minus u squared minus another u squared plus a u to the fourth u squared du, which will be equal to negative the integral of 1 minus 2u squared plus u to the fourth times u squared du, which will be equal to negative the integral of u squared minus 2u to the fourth plus u to the sixth du. Now, of course, finding the antiderivative of this and distributing out the negative sign, we're going to get negative a third u cubed plus 2/5 u to the fifth minus 1/7 u to the seventh plus an arbitrary constant of c. My u, if you remember, was a cosine, so this will simply be equal to negative 1/3 cosine cubed of x plus 2/5 cosine to the fifth of x minus 1/7 cosine to the seventh of x plus an arbitrary constant of c. Let's see, we wanted to find the integral of tangent to the fifth theta times the secant to the seventh of theta d theta. Let's try to figure out how to work with this. Well, let's try to rewrite the integral to be tangent to the fourth of theta times the secant the sixth of theta times the secant of theta tangent theta d theta. We can go one more step with this. We can say this is the integral of tangent squared of theta squared times the secant the sixth of theta times the secant of theta tan of theta d theta. Now, we of course have to recall a property from pre-calculus on what tangent squared of theta equals. If you remember the property that says, or the identity that says, sine squared of theta plus cosine squared of theta equals 1. Out of this, if we divide by cosine squared of theta, we're going to get that this becomes tangent squared of theta plus 1 equals 1 over cosine squared is simply secant squared of theta. So what we can say is that the tangent squared of theta is simply equal to the secant squared of theta minus 1. Let's use this property, this identity, and substitute it back in for this. So we're going to end up getting, so this is going to be equal to the integral of secant squared of theta minus 1 squared times the secant to the sixth of theta secant of theta tan of theta d theta. So now let's use a little bit of u substitution. So let's say u is equal to secant of theta. Then du, we have to remember that a derivative of secant is the product of secant tangent. So we get the secant of theta, tan of theta, d theta. So I can rewrite my integral to be the integral of u squared minus 1 squared times u to the 6th du. Now working out the algebra, this becomes the integral of u squared minus 1 times u squared minus 1 times u to the 6th du. This, of course, becomes the integral of u to the 4th minus 2u squared plus 1 times u to the 6th du. This becomes the integral of u to the 10th minus 2u to the 8th plus u to the 6th. Derivative of this, we're going to end up with 1/11 u to the 11th minus 2/9 u to the 9th plus 1/7 u to the 7th plus an arbitrary constant of c. Our u was the secant, so this becomes 1/11 the secant of 11 raised to the 11 theta minus 2/9 the secant of 9th, the secant to the 9th of theta plus 1/7 the secant to the 7th of theta plus an arbitrary constant of c. Let's take a look at one more problem involving fundamental theorem of calculus. So let's say we want to find the definite integral between 0 and pi of sine squared of x times cosine squared of x dx. Okay. We need to recall the power reducing formulas. So if we have the sine squared of x, this is simply going to be equal to 1 minus the cosine of 2x over 2, which is the same as saying a half minus a half cosine of 2x. Or if you like, you can say this is a half into 1 minus the cosine of 2x. For cosine squared of x, the power reducing formula is going to be 1 plus the cosine of 2x over 2, which again becomes 1/2 into 1 plus the cosine of 2x. So let's use these two formulas to evaluate what this integral is going to be. So we can say that we're going to get the integral between 0 and pi of 1/2 times 1 minus the cosine of 2x times 1/2 1 plus cosine of 2x dx. Now, of course, if we simplify this, a half times a half becomes a quarter, so we can pull out that constant of a quarter out in front of the integral, And then if we multiply the 1 minus cosine of 2x times 1 plus cosine of 2x, we're going to end up with the following. So we're going to get the 1/4, the integral between 0 and pi of 1 minus cosine squared of 2x dx. Now, of course, with this cosine squared of 2x, we can use the power reducing formula again. So we're going to end up with 1/4 the integral between 0 and pi of 1 minus 1/2. I'll put this all in blue so you guys can see it clearly, or in purple. This will be 1/2 1 plus the cosine of 4x dx. So now what we can say is that we have 1/4 the integral from 0 to pi 1 minus 1/2 plus 1/2 the cosine of 4x, which is going to be 1/4 the integral between 0 and pi of 1/2 plus 1/2 cosine of 4x dx. We can factor out 1/2, so now we're going to have 1/8 the integral between 0 and pi of 1 plus the cosine of 4x dx. And of course that we can take the antiderivative of very, very easily. So we're going to end up with 1/8 x minus 1/4 the sine of 4x, which of course is the same thing as saying 1/8 x minus 1 over 32 the sine of 4x. And now we're going to evaluate this thing between 0 and pi. So this is going to be using fundamental theorem of calculus. 1/8 pi minus 1 over 32 sine of 4 pi minus 1/8 times 0 minus 1 over 32 the sine of 4 times 0. This, of course, will give us 1/8 pi. I hope this lesson gave you all some ideas on how to integrate some of the trig functions with certain powers. When we resume in class, I will give you a handout of the basic strategies and techniques on what you should be looking for and how you should go about splitting up the various sines and cosines, secants and tangents and so forth, so they can be very, very easily integrated. See you all in class.